function defined on semi-infinite interval to be the right half branch of an even function defined on the whole real line. Okay? But as we discussed, again, we can regard the same function f of x as the right branch of an odd function. Okay, and so we can apply the result we obtained for odd functions on the whole real line in section 11.7. Okay, so so on the other hand, right, we may regard f of x on 0 to infinity as the right half branch of an odd function on the whole real line. Okay, so we define the fr to be fx for x greater than 0. But because that it is an odd function, so the value of the odd function should be 0 when x equal to 0. Okay. And minus f of minus f if x is less than 0. Okay, so this definition. So you see that the value of an odd function at x equal to 0 must be 0. So that so at this boundary point that f of x may not be equal to f of x at 0. Okay. This is different from here. That for even functions, that the even function has the same value as the original f of function f at when x equal to 0. Okay, so they are different. Okay. This is what you have to know. Okay. And so now we have okay. Because that the function is absolutely integrable. So the odd function is absolutely integrable over the whole real line, and it is piecewise continuous on any finite subinterval of the whole real line, and has the left-hand derivative and the right-hand derivative at every point in the whole real line. Okay, so we have this Fourier sine integral representation. Okay, so we have that. Okay, with BW to be 2 divided by pi of 0 to infinity FR the f of x sine. So I use U sine okay, and which is equal to 0 to infinity of f of u sine w du. Now, even though the odd function and the f may be different at u equal to 0, but because the difference is only at a point, so they will not affect this integral. Okay, so we have that one. So this is for all greater than or equal to 0. Okay, all right, and now, so now, okay, so here, things that so this is implies that things f of odd, if f of x minus, and for all x in this open interval, we have this one. Okay, because of this definition, they are equal when x greater than 0. So they will have the same left limit and the right limit. Okay, so that f x minus plus f of x plus divided by 2 is equal to 0 to infinity b of w sine w of x dw for all x greater than 0. Okay, so just x in from 0 to infinity. Okay, so this one. But how about at the 0? So now, and okay, and you see that when x equal to 0, okay, and because of the odd function, so now we have f minus is equal to minus plus. Okay, because they are odd functions, so they have different sign here. Okay, they have different sign, and so that the average, so this implies that is equal to 0. Okay, so when x equals 0, this is 0. And this can be seen from here. Because when x is 0, this is 0, right? Sine 0, 0. So of course the integral is 0. So you can see that they are coincide with each other, right? This is from the definition of the odd function. And this is from the evaluation of this integral when x equals 0. Okay, so they are the same. Okay, so from here, so now the representation, so that 0 to infinity b w sine wx dw becomes 2 here f of x minus plus f of x plus divided by 2 for x greater than 0, and it's 0 when x equals 0. Okay. Okay, so we have this result. And now we can define Fourier sine transform as we have defined Fourier cosine transform before. Okay, so definition. The Fourier sine transform of a complex or real valued function f on 0 to infinity is defined to be here. So it's f sine transform f square root of 2 pi okay, so if exist. And as you can see that this is just equal to square root of pi 2 and the BW. Okay. Okay. And so we have the corresponding theorem 11.8.b. So the existence inverse Fourier sine transform. Okay, so we let f be an absolutely integrable function, integrable complex or real value function. Okay, from 0 to infinity, and f has its Fourier sine transform. Okay. Okay. So if f is absolutely integrable over this semi-infinite interval, then Fourier sine transform exists. Now, furthermore, if f is piecewise continuous, okay, on any finite subinterval of 0 and infinity, and has the left-hand derivative and the right-hand derivative at every point in the semi-infinite interval. Then we have f of x is equal to square root of 2 divided by pi, 0 to infinity, f hat s and w sine wx and dw. Okay, for all x in 0 to infinity, all right, the open interval, except 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 at a point x0 where f is discontinuous. Okay, there the value of the integral, okay, equals the average of the different radian limit. Okay, and if f0 equal to 0, okay, and the value of the integral at x equals 0 is 0. Okay. And now the right-hand side here will be defined to be the inverse Fourier sine transform. Okay. Okay. So this is defined, which is a function on 0 to infinity. Okay. And call the inverse Fourier sine transform. Okay. Similarly, this is called the inverse Fourier a function on 2. Okay. Any questions? Okay, great. Now, I will state some additional results without proof because I have no time for that. So see linearity of Fourier cosine and sine transforms. Okay, so FG, so they are absolutely integrable on complex our real value functions on 0 to infinity, and alpha, beta, complex numbers. Then alpha f plus beta g is absolutely integrable over 0 to infinity, and the Fourier cosine transform of AF plus BG is equal to A times the Fourier cosine transform of F alpha plus beta Fourier cosine transform of F of G. Okay, so that the Fourier cosine transform is linear. Okay, and similarly, the Fourier sine transform is also linear. Okay, so we have linearity. And a theorem which is important in the study of PDE, the Fourier cosine and sine transforms of derivative. Okay, so so the statement is here. So f is continuous, complex or real valued function on 0 infinity, and f prime right f prime exists and is piecewise continuous, so maybe I will say differentiable, maybe I say. Oh, okay. Continuous. All right. Maybe I, and the f prime piecewise continuous on every finite subinterval. Okay. Okay, so interval of 0 to infinity. And third one, this is continuous. And the f of x goes to 0 as x goes to infinity, right? So the f function is continuous, and okay. Also, we required that the Fourier cosine So if the Fourier cosine transform and the Fourier sine transform exist. Okay, so if this exists, okay, and this is guaranteed. If f is absolutely integrable over 0 to infinity. Okay. Then, okay. So if okay, then the derivative, right, has Fourier transform, Fourier cosine transform, and Fourier sine transform. Right. So first of all, so if the Fourier cosine transform of f and Fourier sine transform of f exist, if these two exist, then the Fourier cosine transform of f prime exists, and the Fourier sine transform of f prime also exists. And we have the following formula, right? So now the Fourier cosine transform of f prime is equal to W Fourier sine transform of f minus the square root of 2 over pi times f0. Okay, and the f of x f prime, okay, is equal to minus W f of CF. Okay. So we have this result. Okay. All right, and it's very important to have this property that the original function f will goes to 0 as x goes to infinity. Okay, so this is required to have such a result. Okay. And f prime, f has piecewise continuous derivative, okay, and which so it's on every finite subinterval, okay. Okay, so the proof. So I have given proof. See lecture notes. Okay. All right, and all right, okay, and also the result on the convolution of two complex or real valued functions on 0 infinity defined as defined to be which is equal to 0 to x if it exists. Okay, so I have defined the convolution of two complex or real value functions on the semi-infinite interval. Okay, if it exists, so the convolution is defined this way. Okay, and you have to note the interval of the integration is from 0 to x. Okay, for all x in. Okay, so the convolution is also a function defined on 0 and infinity. All right, and I have given the existence theorem about in what condition that this convolution exists, and about the Fourier cosine transform and the Fourier sine transform of this convolution. Okay, so please see the lecture notes. All right, to see the results. And so I have to move on to discuss the Fourier transform. Okay. So we will study functions on the whole real line. Because in the previous section we study functions defined on the semi-infinite interval. But in this section we study functions on the whole real line. Okay? All right, so again, we let f of x be an absolutely integrable, okay, complex or real valued function on the whole real line, which is piecewise continuous. So which is piecewise continuous on any finite subinterval of the whole real line, and has the left-hand derivative and the right hand derivative at every point in the whole real line. Okay, so we consider that. Then by the Fourier integral theorem, all right, so we have this result that the average of the left-hand limit and right-hand limit of f of x at every point is equal to an integral, right? Cosine for all x in the whole real line. Okay, so and where AW is 1 over pi f of x cosine omega dx, and b of w is 1 over pi from f of x sine x dx for all omega greater than or equal to 0. Now, you can see the integration here is from minus infinity to infinity, but the integration here is from 0 to infinity. So it is not symmetric, not symmetric like we considered for functions defined on a semi-infinite interval. Okay, so we will develop a formulation such that the integration interval will be from minus infinity to infinity, okay, to get some symmetry. So let's see how we do that. Okay. Okay, so now we will do the substitution. So now okay, this is 1 over pi. So this is from 0 to infinity. So now we put A and the W, AW and BW into this integral. Okay, so we put them back. And so we have cosine. So we go back. Okay, and D, U, and DW. Okay, so maybe I will change the value for U. Right, so this we have has a better look. Okay, so we have that. Okay, so now and this is cosine of x minus u and the du and the dw. Okay, so we integrate over U and then W. Now, when we look at, so this is a function. When we look at here, look here. So it's a function of a W, right? It's a function of W. This integral is a function. So for a fixed, so when and it's an even function of a W. When X is fixed. Okay. Right? So when X is fixed, so we know that. So when X is fixed, then the integral here, so the inner part is an even function of W. Okay. And when it's an even function of W, so that when W is minus, right, then you have the same thing. So we can extend the integral from minus, so we can append the integral from minus infinity to infinity. But divided by 2, I'm sorry, 2 pi. Okay, divided by 2. Okay, so this gives us this. First of all, we have the first step. Is that okay? Good. This is the first step we have. Also, we look at 2 pi and this integral. If we use sine, okay. Now instead of using cosine, we use sine function here. Again, this is an odd function. Of W when X is fixed. Okay, so this is all right. So this is an odd function, and so when the odd function, when do the integration, we see that the result is 0. Is okay? So now we can add something to that, and so for that we can form so now the Fourier integral representation becomes to here okay plus I, right, and this double integral sine okay, it's okay because this is 0. Okay. And So when we're doing so, we have cosine plus I sine up here. All right, and by the Euler expression, we know this is equal to exponential of I and W x minus U. Okay? So this is just this one. Right? So so now, so this is by Euler's formula. The Euler formula says that if you don't know this Euler formula, please raise your hand. Good. So you know that. Very good. All right. So so now we have for the representation. Okay. So here is that we divide 1 over 2 pi by 2 factors, right? So that 1 over square root of 2 pi. And 1 over square root of 2 pi. Okay. And this is f of u. And the exponential function can be written by minus I w and the du. Okay. And the other part, EI wx and the dw here. So now we can write this way. Because this is exponential function. Okay, so you can split into these two factors. All right, and this is for all x in here. And so this integral, so this is called the complex. So you call the complex Fourier integral representation. All right, of f of x. Okay, so it's called the complex because we use complex numbers here. Okay, complex kernels like that. So now we have some symmetry here, and so we will put some definition. So the Fourier transform of a complex real value function on minus infinity to infinity is defined to be okay. and here is E for all W in the whole real line. So we will consider not only positive frequency, but also negative frequency. Okay. So we have, so this is called, if it exists. Okay. So Fourier transform is defined this way. And if the function f is absolutely integrable over the whole real line, then its Fourier transform always exists. Okay, and so we have the theorem here. 11.9.1. If f is absolutely integrable, okay, it's a complex or real. So if f is an absolutely integrable complex or real valued function on minus infinity to infinity, then its Fourier transform its Fourier transform f of f hat, which is exist. Furthermore, f hat is uniformly continuous. Uniformly continuous on minus infinity and infinity. And the limit as w goes to plus or minus infinity, f hat goes to 0. Okay. So of course this is from Riemann-Lebesgue lemma, so you know this as before. And but we still need to prove that f hat is uniformly continuous. Okay, it's uniformly continuous. So the proof. So please see lecture notes. Okay. So I ask you to like the lecture notes here. And so now I will state the existence of it. So that this one so now theorem 11.9.a, existence of inverse Fourier transform. All right, so let f be an absolutely integrable complex or real value function on minus infinity to infinity, and f hat its Fourier transform. Okay, if f is piecewise continuous, on any finite subinterval of the whole real line, and has the left hand derivative and the right hand derivative. Okay, and the right hand derivative at every point in minus infinity up to infinity, then f of x can be expressed by similar formula, but with the Fourier transform. But the kernel is a little bit different. That the exponent, instead of minus here, we put plus. So this is plus here. Okay, this is plus here. And so for all x in the unit, except at points x0 where f is discontinuous. Okay, and there the value of the complex Fourier integral equals to the average. Okay, so we have that, and this integral will be defined to be the inverse Fourier transform of f(a). Okay, so that is a function, all right, on the whole interval, and the code the inverse Fourier transform of f(a). Okay, so we have this one. Okay. Okay, so now, so please read the rest of lecture notes, section 11.9. Okay, so that so in the rest of I will study we still have the linearity of Fourier transform, and we also give a theorem about the Fourier transform of derivatives. Okay, just like we have given similar results for Fourier cosine transform and Fourier sine transform, and also we have defined convolution of two functions defined on the whole real line, and their Fourier transforms. Okay. So that so I ask you to read the rest of the lecture notes, section 11.9, and so next week we will cover the whole chapter 11. Okay, the whole chapter 11, and so I believe that you have received the solution of homework up to number 5. Okay, and so, well, we will prepare the solution for homework number 6 as well as number 7. Number 7 will be given next Tuesday. Okay, before the examination. And we will hand in to you the solutions at the same after the examination, after the quiz. Okay. Any questions? Okay. So I'll stop here.